Welcome to the first session of second tutorial. So today's plan is that I'm going to, address only key issues relating to each questions. And the idea is to give you sufficient direction so that able to complete the assignment without much trouble on your own. So for this, I'll be mostly using concept which you already know because they have been covered in class. So I'll assume that you know most of it and I will not be explaining everything. However, if you see something new which you find unfamiliar, please stop me and ask questions. Okay. And so before we begin, I would like to, so this is a kind of disclaimer that this is not a full solution to any of the problem. Okay. And so sufficient effort is still needed from your side to complete the assignment. And so in the next tutorial, we'll cover the whole assignment. And I plan that it should be like much more interactive, whether both your solutions and my solution should be presented. Okay, so I'll directly dive into the session now. So first question was that you have given a table SFR underscore mass dot fits, which lists the star formation rate and stellar masses of about 300,000 galaxies. And then you were asked to do a bunch of the things. Okay. So related to this question, I'm only going to address 3 key points. And so they are, the first one is reading tables and forming subsets. Second thing is plotting contours, because I think many of you were confused just looking at the Moodle discussion. Most of it was about plotting contours. And the third one was that how to fit a straight line and find the scatter around the best fit relation. So if you know how to do these 3 things, then rest of the questions can be easily tackled because it does not require any other thing rather than kind of skills. So all the techniques that you will employ in solving these things are needed to solve all the questions. Okay, so this is also relevant for solving question 2, but we'll come there after it. So let me just start how to read table and form subset. So one of the advice that I would like to give you, that if you know that you are given a table, okay, suppose in whatever format it is, even if it's fixed format, best practice is to use astroby.table module to handle it. If you use fits.open, you can still do that, but it's not efficient. So I'll strongly suggest you use table, astroby.table module. So in the first cell, I have imported all the necessary modules that I need, and I have run it. And in the second cell, what we are going to do is that first we read the table in this line, and then we read the columns. And so this is standard procedure. It has been covered in your lectures as well. And each column, I'm assigning a variable name, which is represented by the name of the column itself. Okay. So now if we have correctly read the table, if you just create a scatter plot of log M and log SFR, then you should get this scatter plot, which is given in the question. So if this your scatter plot matches this, which means that you're on correct path, and then you can go ahead. So let's see if you do that. So here the same scatter plot we have got. So we have correctly read the table and things are properly defined. Okay, so now how to find the subsets. Now, if you're given a table, the most easiest and convenient way to form a subset is using this function np.where, numpy.where. So what it does is that it takes a condition, and if it allows you to pick elements where this condition is satisfied. The best way to understand is that to see it in action. So suppose now we only want to select galaxies where the log of SFR is greater than 0. So these are highly star forming galaxies, right? So then we define this np.where log SFR is greater than 0. Okay. And I assign it a variable name, high underscore SF, which just tells that we are selecting highly star forming galaxies. Okay. So now what will happen, suppose if you print this, then what it does, it returns an array. And this array contains the row indices of the table where the log SFR is greater than 0. So how to use that? Now, actually, if you have this indices ready, then you can apply these to any columns. Okay. So suppose you want to pick stellar masses of these galaxies where the log SFR is greater than 0. So what you need to do, you just in this column log m, you just under the bracket, you just apply this condition. So this will give you the log m for only those galaxies where corresponding log SFR is greater than 0. Okay. So this way you can select the galaxies which are, which satisfies some criteria, right? So if we have selected our galaxies properly, then if we overplot our selected subset on this, right, only the topmost region will be, selected. So let's see if we have done it properly. So I'll just overplot our selected galaxies on the previous scatter plot. It's running and it has given us a result. So you can see in orange the subset that we have selected, which was all the galaxies where the log of SFR is greater than 0, they have been selected. Okay, so that's how you select subset if we have a table using np.query. Okay, coming to the plotting contours, right? So the rationale behind looking for contours in this plot was that if you just look at this scatter plot, you won't be able to know if there is some region in this parameter space where galaxies are more clustered as compared to some other space, right? And so idea is just to tell you how the distribution of galaxies in log SFR versus log M parameter space. What is the distribution of galaxies in this parameter space? You have been like asked to play with the contours, right? So what contours will do, they will join the regions where the number of galaxies are equal, and hence they will indicate the number distribution of galaxies in this plane. Okay, so as I think everybody knows, in order to create a contour plot, you have to give it a 3 variable. So x, y will be this just axis, mesh defined by x and y axis of log SFR and log m. And on the z, we need to give something else. So since we are interested in finding the number of galaxies distributed in this plane, we'll just give the number counts in a 2D histogram defined in this plane. Okay, so we start by creating a 2D histogram. So we create a NumPy a 2D histogram, and right now I have just kept the bin keyword equal to 2. So what it does, it creates 2 bins along each axis, right? So all in all, the 2D histogram will be a 2x2 bin object. Okay, and it also stores the counts in each of the bins, the edges which define the which actually defines the bins, and so these things are stored here. So we can just plot and see what is happening. Right. So you see that we have like asked this histogram to create 2 bins along each axis. So that will mean that it will give 3 points in this x edges and y edges variable. Why? Because like 3 values are needed to define 2 bins, right? Because one will be from 7.25 to 9.67, and the second will be 9.67 to 12.08, etc. However, the histogram itself is a 2x2 matrix, right? So each bin will contain 1 count, which corresponds to the number of galaxies which are there in that particular bin. Okay, so notice that if you want to create a mesh grid using this edges, the value of edges, you cannot do that because here you have 3 element in one array. So if you create a mesh grid, it will be like 6 cross 6, right? Although the histogram that you have is like only 2 cross 2, right? So if you try to create a mesh grid using just edges, it will give you an error message. It says type error because shape of X and Z do not match, right? So what to do? See, what we can do is that, so imagine that this is our histogram grid that we have, right? So X0, X1, and X3 are just the edges of the bin. And the C0, C1, C2, and C3 are the counts in each bin. So now what we want to do is that assign one X value each of to this C's, right? So what we can do that we can assign bin center, right? So we'll find the median of X0 and X1, right? And we say that corresponding to this X0, the mean value or bin center of this, the galaxy count is C0. And that's how we'll proceed, right? So the bin centers are nothing but the midpoints between the bin edges. And so clever way to do is that using this line. So in this one single line of the code, you can get the bin centers for all the bins that you have in your histogram, right? So again, we start with, let's say, for demonstration, a very small number of bins. So then what happens? Let's try to understand what is happening. So when this first expression actually is the all the bin edges that we have. Okay. The second expression is bin edges, but excluding the last one. And the third expression is the bin edges, excluding the first one. Okay. So now what will happen if you just add these two arrays and divide is that essentially you are choosing a value in between 7.25 and 9.76. So essentially you are creating rather finding the bin center for each of these bins, right? So that's how you find it. So now we'll just change this bin size to, let's say, a large number, let's say take 30, because we want to sufficiently, we sufficiently want to sample the log SFR versus log in plane, and we'll run this code. So the bins, etc., are divided. So once the centers have been created, you can use this to create the mesh grid, right? And then proceed in the usual way to plot the contours, right? So in this plot, I have overplotted the contours on the scatter plot. Okay, so you just are adding. So X and Y are the are the mesh grid parameters, and on the Z I have like given the counts. Notice that I have put a transpose, and this is because if you don't put transport, the sense of plotting of this scatter plot versus this contour plot is different. I think Yogesh has covered this in his lecture that each code kind of it has a preferred direction. Some of them actually prefer to pick X first, and the other ones they prefer to pick Y axis first to plot. So the sense of plotting is different between scatter and the contour. Hence, I have to transpose it in order to make them in the same sense, right? So once you do, you get this. I'm using this default value. I have not chosen any labels. Of course, you can play with labels and refine this plot, but I leave that to you. So here you see that there are two peaks in this distribution. One happens at high SFR region, and one happens at the low SFR region. So it just tells you that galaxies in this parameter space, they form a bimodal distribution. Okay, so this was done. Now we come to the third key point, which is to fit a straight line, and we need to find the scatter around the best fit relation. So this was, I'm doing this because you have been asked that you need to, kind of get the, pick only star forming galaxies and fit a straight line and find the galaxies which are outliers from this best fit relation at 3 sigma levels. So what will I show you? First, I'll pick the galaxies only in the star forming region. And the star forming region was defined where the difference between log SFR and log M is greater than or equal to minus 10.8. So this definition has been given in the question itself. So we pick the star forming galaxies. We find all the galaxies, the stellar masses and star formation rates of these star forming galaxies. And then what we do, we just create a scatter plot first. Okay, so if we create a scatter plot first, it looks like this, right? So notice that galaxies in the star forming region, they kind of they seem to follow a linear trend, right? And you are asked to fit a straight line to this relation. Okay, so fitting straight line is very easy. So what I am using is that I am using a function called stats.linregress, which is a linear regression from the statistics module of the SciPy. So we import this on the top of our code. And then what you can do that within stat.linregress, you just provide your X and Y arrays. And so what it does, it fits a straight line and it also gives you an intercept and a slope. Okay, so if we just run this, then fitting has been done. And these are the value of intercept and system. So once that is done, what we can do is that we can overplot this straight line on this scatter plot. So this we will do next. So to plot the best fit line, this code is there, right? So I'm just using plt.plot x array and the slope and intercept. So this is just y equal to mx plus c kind of equation of the straight line which is there. So now we'll just run it and see what happens. So this is your best fit line, which is here. So right now, you might think that this fit is not that great because it's kind of slant, although you see the scatter plots are maybe much more steep. But that's not the case because again, you're not seeing the density distribution of this points in this plane, right? So a simple way to do this without having to use the contour plot is you can just simply plot a 2D histogram of all the points in this parameter space. So that can be done using plt.his2d, right? You can choose a number of bins. We have chosen like 50, which is a large bin because we sufficiently want to sample the region, and then we just plot it. So let's see what happens. So now you see, so this color bar actually shows you, it indicates how many galaxies are there in each bin. So like more yellow is, number is high. So you can see they're mostly clustered around here. And now this best fit line does not seem that bad. Okay. So now if you want to know the scatter around the best fit relation, what you just need to do that from the SFR, you just subtract this straight line. Okay, the equation of straight line. So whatever you will get will be a residue, right? And for a good model, the residue, the mean should be somewhere around 0. And then it should be randomly scattered around this mean, which is closer to 0, right? So if you just want to know what's the mean and standard deviation of this residue, you can just use np.mean because now remember this is an array, right? So you can employ, you can use all the NumPy functions which can act on arrays. So then you comes like this, right? So now this is done. And so if you know all these techniques, question 1 can be easily done. Okay. So there is nothing else because rest of the questions also require you to somehow form subsets and do some basic array manipulations or fitting on it. So if you know all these 3 things, you will be able to do this. So one announcement is that after this tutorial, I'll make this notebook available. so that you can refer to it. So wherever, if you're stuck, there are these hints which are there. There are the methods which are already present. Using them, you can answer all the questions on your own. Okay, now coming to the question 2. So this question is also very similar in spirit to question number 1. Again, you have to like form subsets and do some array manipulations. The only difference is that now you have to create a separate table, right? And so here you are given 2 tables and you need to join them using join sky code, right? So this is 1 line of code, and if you just go to the Astronomical documentation and see how to join tables using sky code, you will get the answer how to do that. It's very easy. It's 1 line of code. So I'm not going to cover it, right? And rest of it, again, since it requires just a creation of subsets and some array manipulations, which all the techniques which I have already shown you, I'm not going to talk about these questions anymore. So I encourage you to try this problem, and if you still feel difficulty, I'll maybe in next tutorial session I will tell you how to do it. Additionally, I have also given extra hints which were not present in the previous in the assignment, in the original assignment, in the way that I have given you. Okay, so here there are very detailed instructions on what to do if you get stuck. So I think this question then becomes very trivial. Okay, right. So this is done. So now we go to question number 3. And again here, this question closely follows the material which was taught in lecture 10 on model fitting. And I encourage you that you refer to the video and try the same sequence of steps. The only difference is that now we have 2 Gaussians, one with positive and one with negative amplitude. Although in the lecture demonstrations, you had 2 Gaussians where both of them had like positive amplitude. So I will even point out where you can find this. So let's see. Right. So this is the slide of question. The lecture 10, and so this was your. I mean, you can treat this as a problem spectrum, and you will fit it. So all the steps which are shown here, you need to follow the same thing, right? So instead of Gaussian with amplitude, let's say some positive value, you just need to provide some negative value. So only thing that you just need to think here is that to give suitably chosen these value means and the standard deviation, etc. They'll be different. So depending on you provide a good guess to these parameters and follow the same sequence of steps till here, and you will just do it. It's very easy. Right. So what I'm going to demonstrate you next is that how to play with these images. So in this problem, we had given this image, which, and there were 3 galaxies which were aligned diagonally, and you had to find a few things and perform a few exercises. Okay. So here, again, this question can be dealt very easily if you know 2 things. First, you need to know how to slice image data. And the second thing is that how to find the brightest pixel in a given region and its sky coordinates. If you are able to do these 2 things, then the rest of the problem becomes very easy. You don't have to struggle at all. So maybe I'll show you that, right? So we start by reading and opening the image file. So this is the image file that we had given. So now we just read this using fits.open and display its header. So notice that this is a multi-extension file. So it has like 4 extensions. Although on the extension number 1, all the data is there. So we'll mostly work with extension number 1, right? So we read the data of extension number 1 and we display what kind of object it is, right? So this is actually an array of 2 dimensions. So you can just think that it's a matrix defined by number of pixels on both sides, and each cell contains a count which is related to the brightness of objects in the sky, etc. Okay, so in the problem you had asked that find if some basic statistics, find the mean and find if there are any negatives present or not. So given this information that you now have, that this is nothing but a 2-dimensional array, you can use NumPy module to get the mean, median, minimum and maximum values. So I just leave it on you. You simply apply np.mean, give the data, and it will give you what's the mean value, what's the minimum value, etc. Right. So right now I don't know whether this image contains any negative values or not, that you will find. But suppose I'm assuming that there are negative values, and if there are negative values and suppose you want to replace all the negatives by 0, then what to do? It's very similar in np.where spirit, but now what you have to do is that you just apply this condition that within this data, wherever the data is less than 0, I'm putting the a 0 value. So all the pixel which contains negative value, the values of those pixels will become 0 now. Okay. So now what we do, we just try to display the image, and notice here I have added a small number because now by my construct the minimum value was 0, and I'm trying to show this image using a log norm scale. So you cannot use with 0 because there is a logarithm involved, because that's not defined. So hence we'll go with it. So I'll just display this data. So now you can see everything is there. Okay. So now suppose we want to find the central position of this galaxy, which is the top on the top right corner. And in the question, you have been told that consider the brightest pixel in the central region of that galaxy as its representative pixel, a pixel which represents its position in the sky. Okay. So in order to get that, what we do first, like we will slice this image data. So I know that this galaxy is somewhere around this top right corner. So it will be bounded by some regions, right? So on the y-axis, it's definitely above 250. On x-axis is also, it's definitely after 250. And I also go till, let's say, 300, right? So convention here, remember, is that in the images, always y first, then x. So writing this actually means that this will pick only data from pixel range y min to y max, which is y equal to 250 to y equal to 300. And then x min, x max, x min 250 and x max 300, right? So if you just pick that area, okay, and you define a variable which will denote that data, and then if you plot that data, what will happen? You should get this galaxy only, so which you are getting. Okay, so now our next job is just to find where the maximum of what is the location of maxima in this array, right? Because remember, all the data that we are playing with are just an array, right? So again, all the functions of numpys can be used. So location of maximum for an array can be found using np.amax. So it just tells you, just give an array, so it will tell you what is the maximum value of that array, right? So this gives you what is the maximum value in this image, right? And then I'm just applying np.where, wherever this data has that maximum value, you pick that pixel number. So that will give you the location of brightest pixel. And again, since it's an image data, it's always y first, then x. I'll just print the x and y location using this, right? So in this kind of chopped or sliced image data, we know that the brightest pixel is at 34 on y, and like x coordinate is 26. That's the pixel number. Okay. But remember that we had chopped this. So originally it was started from 0, but now we had chopped this. And so here 0 became 250. So what we just need to do is that we just need to convert it back in the, the whole coordinate systems. And so we just add it back 250, 250, because that's how the origin was defined. Okay. Right. So this then becomes the x and y. The origin rather than the position, the representative pixel which will define the sky position of this particular galaxy. Okay, so in order to get it into convert this into array and deck, okay, what you need to do is that you can use the WCS function from AstroPy module. So you can import this. And inside this function, you can just put the header of this extension, which you are using. So this header contains all the information and conversions between pixel to sky coordinates. And WCS is that just reads that and stores it. And then you just use this function again from pixel to world. So what it does, once the WCS conversion has been read properly, you just supply the x and y parameters, right? Because x is towards the array and the y is towards deck. So that's the convention. You supply your x first and then y, and then it will give you the coordinates. So the coordinates here of this central region is in degree is 217.553 and minus 0.839, etc. Okay. Just to check if you have done it rightly, I have just opened this image in this software called DS9. So we'll zoom it towards the center and see if we have done it correctly. Okay. So let us try to zoom. And I can play with the brightness. So roughly this pixel is the brightest. So just notice the number in this alpha in this WCS panel, right? So it's 217, maybe here, 217.5539. So it's very close. And the deck is also minus 0.8379. So we have done a good job. Okay, so similarly, you can find the array and deck of other galaxies. I think you have only asked to do this galaxy, and this one. And once you have got it, you can find the separation and everything else which are there in this question. That's, I think, is very straightforward. You need some geometry, and sometimes you may also need to use a function called separation in the AstroPy module, just to get the angular separation, etc. But I think that is again covered in the has been covered in the lecture. So I'll again leave the rest of this question to you. Okay. Now we come to the last question.
Preetish, before you go to the last question,
yes.
I just had one additional comment here, which is we've asked you to assume that the center is at the brightest pixel.
Yes.
That is a very reasonable first assumption. But if you want to get more sophisticated, you can try to find the centroid of the central region. So you will get a sort of fractional pixel as the centroid. And then that will be a more accurate measure of the position of the galaxy center. So this is just a sort of add on to the question. The question itself expects you to just find the brightest pixel.
Okay. So should I go ahead then?
Yeah, please go ahead.
Okay. Now coming to the last question, this was actually a fun thing to do, and it did not like it does not require you to do or even know a lot of things. So you just need to find a module which will create an RGB image if you are given, um, images of a galaxy in 3 different filters. So that have been given to you, and you just need to download this data. And first you need to, download the data and read the images. So the red channel is here, the bright green channel is here, and the blue channel image is here. So just read them. And what you just need to do is that from astropy.visualization, you can import this make lepton RGB function. And in this lepton RGB function, you just apply these, just read the data from these and just apply it. And it will create an RGB image for you. Okay. So only extra thing that you need to take care of, what happens is that, when you take the observations in different bands, sometimes what happens is that in one channel you might, you might have taken some deeper observation, right? So suppose if you assume that in this data that we have given, you have taken deeper observation of green channel as compared to other two channels. So if you just simply supply the RGB data here, then this lepton RGB will give you image which is more green because it's very dominated. Okay, so we need to need to normalize it. We want all the counts in pixels of all 3 images in similar ranges. So for that, what I have done is that I have just divided each data by its mean. So everything is in, so that across all 3 images, the counts kind of become comparable. So once you do that and just apply it here and just run this code, this takes some time though, because each of the images are around 400 MB. So I think it will take 4 or 5 minutes, and then it will give you depending on, of course, your computer, it will give you an RGB image. So let this run for like 5 minutes and we'll get an image. But in the meantime, if you have any question, please ask, because this is nothing. This will just.
I'd just like to add a comment, which is how do we know that this cell is running? Because the number, like where you have this in square bracket, there is a star after that. That indicates to you that this particular cell is actually running at the moment. And if you try to run all cells together, then you might have a star for all of them. Anyway, yeah, you got the image.
So you have got the image. So that's how. And so it saves as well in your local directory wherever you have done it. So let us try to see as well.
Yeah.
So this is the image that you want. The resolution is very high, so it will just take some time to load, but it should be coming anytime. Okay. Yeah, it's there. And so you can zoom in and see all the different structures and wonder about galaxies. Okay, so that's it from my side. I will take any questions if you have, or like if you have any doubts or facing any other difficulties in the assignment.
Hello, sir.
Yeah.
Sir, whenever in question 5, whenever I'm trying to run this set of codes, my computer is getting hanged.
Okay. So what
I first tried to plot only the images from each channel, and they took about 1 minute time to be plotted. Then when I am using the make lepton RGB function, then the computer is getting hanged, and it has happened about 4 to 5 times. As many times I have tried to run the program.
Okay, it might have to do with your. It depends on your machine, because it's like.
I'm using Windows 10.
No, it depends
How
on your
much,
RAM.
how much RAM do you have?
Sir, I have to see that.
Okay,
So if
but-
you have RAM less than about say 8 GB or so, it can cause trouble. So you may, instead of, if you have access to a desktop, usually desktops have more RAM. So you can try there instead of laptop.
No, sir, I don't have a desktop immediately.
Okay, so I suggest the following just to see if your code is okay or not. Just like we had sliced
Okay.
that image, right? From, let's say, in some range. We had done this, right? This slicing
Yes,
kind
yes,
of
yes.
stuff. You also do a slicing and you do equally for all the three images or the
Okay.
datas, and just make a left and RGB and see if you are getting.
Okay.
Okay.
Okay, thank you. Sir, I also had another question about question number 4, where we had to find the brightest pixel in a galaxy. So it is possible that we have an image where there are about like 100 galaxies or so, and
Yes.
in that case, if we have to slice 100 times and find the brightest spot in the center, then it will be very time consuming. So is there a function that can do this
Yeah. So
automatically?
okay, I'll answer this question, but before I'll tell you what's the motivation. So motivation for giving this is that you're just playing with arrays and you're doing it on images, and it's practical and hands-on. And so there are different modules which essentially do the same thing in very faster way, where you don't have to do everything by your hand. But just to know what they do, you need to do some things by your hand. So now you know how to do it. So you will get the idea if some function is given to you, how does that perform. So in order to detect images, various galaxies, let's say big image or whatever, a very excellent module exists. It's called photutils. So you can supply it an image, so it detects all the galaxies or all the sources which are there, stars, galaxies.
I was actually looking into this 40 utils module, but I didn't know that whether I have to use that in this question or not.
No, you don't have to. You don't have to.
Okay.
So, like I said, all the questions that are given to you can be tackled by the knowledge which have been provided to you through the lectures. You don't need anything additional.
Okay. Thank you.
Yeah, if I may add, I've just added in the chat link to the photutils source detection documentation. So you can go through it, and photutils really is a very excellent affiliated package. I think it's also a coordinated package of AstroPy, and it really does many things for which until recently one had to use external packages. But remember one thing, that if there is some functionality in photutils which is not if there is some missing functionality in photutils with respect to what you need, you can also call external programs. So one of the biggest, most commonly used external programs for source detection is something called source extractor. And you can download it, install it, as it's a C program. You can compile it and install it, and then you can call it from within your Python program, and then read in that catalog. But I think for very simple stuff like just finding finding stars, galaxies, and doing photometry on them, photutils is a very powerful module. There is also something called specutils, which is similar to photutils, except that instead of working on on images, it will work on spectra. So between specutils and photutils, you'll be able to do a lot of things.
Yeah, so
Thank you, sir.
I'll just add a line to that. So photutils is now like developing rapidly, and from the version 1 to version 3, a lot of things have been added and improved. Yogesh just mentioned, for example, this software called Sex Extractor. So all those things are already been incorporated. So they have defined functions which exactly act as sec extractor inside the FORTITIS itself. So you can just do it in just Pythonic way. But yeah, like knowing how to call other softwares into a program and use it is also a power of Python, which someday you should learn, like just play around with it and learn. Yeah.
Okay, sir.
Sir, I want to ask for spectrum fitting, we use .pha and .pi files. So, can we open these files using Python?
Are these X-ray spectra?
Yes, sir.
Okay, from Astrosat or some other?
Chandra.
Chandra, okay. So I don't know the answer, unfortunately, to this question, but it should be possible to convert these files into a fits table. Okay? And the moment you convert it into fits, it will be straightforward to read them into AstroPy. Did you try to Google for a solution to this problem?
No, sir.
Okay.
I was just asking now.
Yeah. No. All of these things are, see, what has happened is the X-ray ecosystem, the X-ray data processing was happening mostly in a proprietary software called IDL for many decades. In fact, IDL was developed by X-ray astronomers and software developers. So there are few things, data formats, etc., which are used in X-ray astronomy, which are not sort of non-standard. But I think by now there must be routines for converting those things. There may even be Python routines. What format did you say? Well, can you repeat that once again?
PHA files and PI files.
PHA and PI.
No, I could add that it's most likely fits. You should try the fits module and try to open it.
Okay.
You'll see that it's very likely it's fits. I've used those in the past. Normally, do you use FV tools to open it or no?
Sir?
Have you used any other software to open
Yes,
these files
sir.
before?
Expect.
Okay, but have you ever used DevTools?
No, sir.
Okay, never mind. But most likely these are fits files. Just use the fits module and try to open it. It should be all right.
Okay, sir. Thank you.
So these sort of event files where you have a table with every photon recorded, the time it was received and its energy and things like that.
The original data file is events file, but these PI are just spectra. So they'll have like a bin and KVs, and then it'll say how many counts in those KVs. So it's like two columns.
So there is a good chance they'll just read as fits.
Yeah, it is. It has to be that.
Yeah. Because I was just looking in AstroPy, the raw Chandra data, which are these event files. I think there's a format called MEF format, and that can be read in AstroPy utils.data. Can be used to download these files, and then astropy.io.fits and astropy.table, they work perfectly well.
So can we have a tutorial on PyRaf? Okay.
So this is something that we should need to discuss further with the organizers of this course, because I think we have now reached a stage where you guys should become comfortable with Python, be able to use it. But beyond this point, there will be some people who will be interested in, let's say, optical data processing. They may be more interested in IRAF. But if somebody is interested in radio data processing, they'll be interested in something else. And same for X-ray processing. So we will not be able to have a general purpose course for everyone. But if we want to do maybe 1 or 2 lectures on each of these things, we can do one or 2 lectures on CASA, 1 or 2 lectures on PyRAF and so on. I think that is worth considering, but that would be a sort of advanced course where the prerequisite will be that people have done this course and have done the assignments, etc. Because without that, it will be very difficult for you to follow what's going on in that more advanced course. So yes, we can consider it, but not within this course.
And also, I think people need to have like some background in astronomy as well, if you're going for that.
And one more point I'd like to add is that some of the things that capabilities which are there in IRAF, okay. For example, there used to be an IRAF package called ccdproc, okay, which was used for CCD image data processing, all the usual stuff of subtracting the bias, flat fielding the image, etc., etc. Now there is a AstroPy affiliated package called ccdproc, which provides the exact same functionality. And so you can use that. That is a more modern implementation. It's a more Pythonic way of doing things. So for several things, I would suggest that instead of using PyRAF, which is not really state of the art because it's based on IRAF, which is now a relatively old software, you can go directly for ccdproc, specutils, fortutils, etc., which are native Python AstroPy based, AstroPy ecosystem based packages, and use them. So therefore, I would not strongly recommend something like PyRAF. On the other hand, a package like CASA, for example, which is used for radio astronomy, interferometric data processing, that is in very active development. And so that can certainly be used, and one should encourage people to take it up.
Right, so more questions. Can we do this assignment in Google Colab? Yes, I think you can do it. It's not a problem. You can, wherever you can run a code, you can do it there.
The problem will be with the last question of that RGB thing.
Yeah.
You don't have enough disk space to download those images into Colab.
That's true. What we can do is that we can just supply a small galaxy if we just want to make an RGB. So instead of AM51, you make some other galaxy just to see if your code is fine or not. There is one more question about installing dust maps and HealPy package. Okay, so installation, I don't know, it depends on a lot of things, right? Just check the dependency of these packages and try to figure out. I don't think I know much about these packages. Okay, so one comment is that since we do not know many of the answer to the assignment 2 questions, it is difficult for us to understand whether our code is working or not. See, as long as your code is not giving an error and you are getting some answer, right? I suggest that you go ahead and just note it down, right? And of course, there are some sanity checks. Suppose I ask you to get the fraction, and the fraction will always be less than 1. Or if you're converting in percentage, it should be, mostly it should be less than 100. So if you're getting some 1,000 or maybe 1,000,000, that's wrong. So basic sanity checks, and if the code is running, just go ahead and then we will see. Because I'll be presenting the full solution anyway. So we'll see whether it's correct or not.
Yeah, just to add to this is that Preetish has also suggested independent checks. For example, in that where you had these 3 galaxy images, he said just open the file in DS9 and zoom in and see where the center is, and see whether the coordinates that you have got are similar or very close to what you are getting visually. And that is why I, in my class, in one of my slides, I said that there are 3 tools that you should probably learn how to use for doing data analysis in astronomy. One of which is Topcat for handling catalogs, Aladdin for handling images and also for downloading surveys, survey data from various surveys. And the third one was DS9, because that DS9 is a very quick tool for doing these simple sanity checks.
So, okay. .py files, I think this has been answered. I tried to do first question using fits.open. Okay. So that's why I said that when you know that you are given a table, and so this table has been given in fits format, hence maybe you got confused, but most of the time table can be some other format, right? It can be a .csv file or maybe a ASCII file, right? So, but when it is specified that this is a table, you try to open it with astropy.table module. So then it's very hassle-free. You don't have to struggle a lot. I don't think there are any other questions. Yeah, so work on these. I'll just make this available as we can, and just like even if you cannot complete the whole assignment, at least get started with it, finish some of them, and then we'll see what happens in the next tutorial.